Today we are going to discuss chapters 4 and 5. Chapter 4 is scatter plot and correlation. Chapter 5 is simple linear regression. Now in these two chapters, we are trying to model two random variables together. Of course, in this class, you will not see more than 3 chapters to deal with more than one random variable at a time. So here you have 2 of those 3 chapters. In all 3 of these chapters, we will only model 2 random variables. They are only about simple linear regression. To model 2 random variables, we can come up with hundreds of millions of different equations. What we basically do is, we collect a data set consisting of both random variables. And we are going to see if there is a linear relationship. Now in stat class at intro stat level, we only see if there is a linear relationship existing between the 2 random variables. So we have to be clear about what are the linear relationships. So let's look at that. I have written it down under point number 1. In intro stat, we see only the linear relationship between 2 random variables. Let's go to point number 2. Here we are going to understand what are the linear and non-linear relationships in mathematical terms. A linear relationship is, of course, one random variable is labeled as x and the other random variable is labeled as y. Of course, you can see that one random variable can be taken onto x-axis, the other random variable can be therefore taken onto the y-axis, and then you can deal with OXY plane graphically. First, we will define the linear relationships. Linear relationships are defined as any first order linear combinations of the 2 variables x and y. Any first order. First order means linear. Combination of x and y. This means, technically speaking, all straight lines. No any other shapes. In general, you can write it as y equals mx plus b. In your calculator, it's written as y equals ax plus b under one function, and under another function, it's written as y equals bx plus a. At chapters 4 and 5, we will use the first format, which is y equals ax plus b, and in the future, which is actually after exam 2, we will use this form for a different purpose. Alright, so in mathematics classes, we saw this equation, y equals mx plus b, where m is the slope and b is the y-intercept. The same thing, we're going to see it as y equals ax plus b in this class. And on the other hand, we have slightly modified practical looking definitions for a and b, rather than just the technical definitions such as slope and y-intercept. So any first order linear combination between x and y can be therefore considered as a linear relationship. So one example could be y equals 2x plus 3, or y equals negative 3x plus 1000, and so on. Okay? So you can come up with so many such equations. It's also equally important to figure out what are the relationships that are non-linear. Those non-linear relationships are not modeled using the methods discussed in intro stat level. Okay? So in case if you see a non-linear relationship, you have to know that our methods will not detect those non-linear relationships, especially if there is a linear relationship existing between 2 random variables x and y. There are 2 basic methods that we can detect them. One method is the graphical representation. The other method is the analytical representation, for which we don't need any graph. Of course, if you have a graph, even if you have a non-linear relationship, it can be detected. You can just by looking at that, if the graph has a nice linear shape for the data points, it is a linear relationship. But on the other hand, if your graph doesn't have a linear relationship, but it may have some other relationship. Now this is a relationship, but it is not linear. It is a non-linear relationship. It's a parabolic relationship. The two methods that I mentioned, one of them, of course, will show us that there's a different relationship between the two variables, which is the graphical method. The other method, the analytical method, will not detect any relationships other than the linear relationships. Okay? But on the other hand, even if your analytical method says there's no linear relationship between the two variables x and y, we cannot conclude that there's absolutely no relationship between the two variables. We can only say there's no linear relationship. But there can be any other form of a relationship which is non-linear. So we'll also just quickly see what are the non-linear relationships. So the non-linear relationships are any different than first order equations. For example, y equals square root x. Now this is a non-linear relationship. It's defined for positive values only, and if you have a graph, it can be seen like this. And y equals x squared. Now this is also non-linear. This is not first order. So x squared, we all know that it's a parabolic relationship, not a linear relationship. And if you look at x squared plus y squared equals 4, what is this? This is a circle, right? Center is 0, 0, and the radius is equal to 2. And that's not linear. So these kinds of relationships are called non-linear relationships, okay? Any non-first order relationships between x and y. They're called non-linear relationships. Our methods, especially the analytical method, will not detect any of these relationships. And there's another category. That category is no relationship, absolutely no relationship. There's no linear relationship, there's no non-linear relationship either, which means if you look at the data set, x and y, and if you take one variable onto x-axis and the other variable onto y-axis, then the graph or the data points of that situation will be just like a scattered cloud. It could be just everywhere, you know. No detectable solution, no identifiable pattern. Just the data points are everywhere. So that kind of things are called no relationship. What you have to remember is our analytical method will only tell you whether there is a linear relationship or not. If our analytical method says there is no linear relationship, but between x and y, there can be a non-linear relationship, or there may be absolutely no relationship as well. Let's move on to the point number 3. What are some examples of variable combinations which may have linear relationships? Now that's also important for a reason. The reason can be discussed under point number 4. What are the likely variable combinations where there can be a relationship? For example, the most popular example in all STEM fields is F equals ma, force and acceleration. They are related. Okay? And how about smoking and age expectation? Well, they may be related. If there is a relationship, the statistical methods in these 2 chapters will tell us what is that relationship. And air pressure and altitude. Of course, you know, as the altitude increases, the air pressure drops. So there must be a relationship. Is it linear or not? Well, if we have the data set, then we can use our techniques and see if there is a linear relationship. Now, some possible other variable combinations are engine capacity and highway mileage. They are related. Inflation and bank interest rates. As inflation increases, the bank rates increase. Weight and risk of heart attack. Some people say as the weight increases, the risk of heart attack also increases. So likewise, there can be hundreds of thousands of variable combinations where we suspect there's a linear relationship. In such cases, what we have to do is we can simply go ahead and collect a data set, then use the methods that we are going to discuss in a minute, figure out that relationship. Now let's go to point number 4. Now there's a small risk of statistical methods that we're going to discuss. The risk is the statistical methods will always provide you an equation between two variables if you input the data. Why it is a risk? The problem here is this. Statistical methods will not analyze the science behind the two variables. Why the two variables are connected or not will not be scientifically analyzed. Statistical methods will only give you a mathematical equation which relates the two variables. That will always give you an equation as long as you just input x and y data points. When we select two variables to figure out any relationship, we have to be smart. We have to be careful and select variables that make sense when considered in combination. Sometimes people select silly variables. For example, think about two variables such as the height of the President of the United States and the inflation rate. Now, if you have a data set on that, we can feed the data set into our software and obtain an equation, linear relationship. But that doesn't make sense. And also, if you look at the number of civil engineering doctorates offered and the per capita consumption of mozzarella cheese, they are nicely related as a linear equation. So as students who are learning statistics, we have to be careful when selecting the random variables, especially if you are doing any research involving relationships between two variables, and if you need to accommodate any of the regression methods that we are going to discuss in interest at level, please make sure that you pick the variables that are scientifically making sense when considered in combination. Let's go to point number 5. Now you have a data set. There are two variables. Now how do I label one of them as x, the other one as y? That's one possible situation, and the other situation is you know the two variables by names, and you have not yet collected your data set, and you need to label x and y variables. Now how can we do that? It's done using a little bit of scientific knowledge regarding the variables. So the variable x is called the explanatory variable. Also called in mathematics the independent variable. That means the person who collects the data or the person who designs the experiment has some control over this variable. For example, if I need to find a relationship between air pressure and altitude, maybe I will take altitude as x, because I can control the altitudes where I will take the air pressure readings. At 0 meters and at 100 meters, at 200 meters, at 300 meters, and at 400 meters and 500 meters. Likewise, I can assign the values that I like for this variable. On the other hand, the air pressure, I can just observe air pressure at these altitudes. So the variable y is defined, it is called the response variable, or in mathematics it's called the dependent variable. The The reason why we call it the dependent variable is because it's going to depend on these selected x values. Or in statistics, we call it the response variable because that's the response I'm going to collect, okay, at these x values. So I would say air pressure. So I don't know what's the air pressure at this level and what's the air pressure at this level, the other levels, and so on. So I need to find those values. So that's the basic guideline of labeling x and y. We label x as the variable which we have some control. And the variable y is the response variable or the variable that you have to go ahead and measure. But in some engineering applications, the life is not as straightforward as that. Sometimes we can't straight away figure out which one I can control more easily and which one I have absolutely no control. In such cases, to determine x and y, some sort of subject knowledge will be required. And at introstat level, the students are not expected to have that subject expertise. So, one thing good about this class is those two variables will be very clearly defined unless they can be very straightforwardly understood. One straightforward way to understand the explanatory variable is just to look at the step size. There's a fixed step size. If there is a fixed step size, it is almost always the x variable, okay, explanatory variable. The variable without a fixed step size is usually the response variable. But not every explanatory variable has a fixed step size. For example, we will see a data set today, and that data set doesn't have nice step size for any of the two variables given. So in that case, we need some subject knowledge to figure out the variable labels. And therefore, I have clearly defined which one should be taken as x and which one should be taken as y in that example. So everywhere in this class, whenever x and y are not explicitly clear, I will specifically define which one should be taken as x and which one should be taken as y. So please make sure to read the question carefully and figure out x and y. Because if you mix x and y, entire analysis will be totally incorrect. You are going to get completely different numbers and you will get 0 for the entire question. So selecting x and y, labeling x and y correctly will be critically important. That's the most important part to start the questions under these two chapters. We said when you have an x variable and another y variable, there can be a linear relationship or any other relationship, or there may be absolutely no relationship whatsoever between the two variables. So how do we determine whether there is a relationship? Now that's a really complicated story. But if I ask that question again in a simpler way, how do we figure out if there is a linear relationship between the two variables? Now that's a very straightforward question. That's a question we are going to answer now. Okay? There are two ways to figure out the linear relationships. This is given under point number 6. So how do you figure out the linear relationships? The most straightforward, the simplest way is a graph. You can take x variable, the variable x onto the x-axis and the variable y onto the y-axis, and then draw a scatter plot. Scatter plot means you will always have data as pairs. You know, you have an x reading and corresponding y reading, and you have an x reading and corresponding y reading. That means you can always show them as nice coordinate points on xy plane. So if you have a nice linear relationship just like that, when you do the data points on x and y axis, then we can say there is a linear relationship. So a graph like that will be called a scatter plot. So the first method to figure out if there is a linear relationship or not is a graphical method. So the graphical method is the scatter plot. Just look at the scatter plot and see if it shows you a nice linear shape between x and y. And then we also have something called the coefficient of correlation, which is the analytical method. So the analytical method is, this is the graphical method. The analytical method, we are still under point number 6, okay? The analytical method is to calculate the coefficient of correlation. The statistical label given for that one is R, lower R, okay? That's the coefficient of correlation, also called Pearson's correlation, coefficient of correlation. And the coefficient of correlation is a value between -1 and +1. And the coefficient of correlation, if it is close to 0, we say there is no linear relationship between x and y. Remember, we don't say there is no relationship between x and y. We only say if your r is approximately equal to 0, there is no linear relationship between x and y. More interpretations of R can be seen in a minute. Let's move on to the next point, which is point number 7. Point number 7, we discuss the two types of linear relationships. We can have increasing linear relationships or decreasing linear relationships. Increasing relationships, they're also called positive linear relationships, and decreasing linear relationships, they're also called negative linear relationships. So what are these two types of linear relationships? We said we have two methods to detect, the graphical method and the analytical method. So the graphical method, if the scatter plot shows an increasing pattern overall, it's an increasing relationship, which means the coordinate points should be like this. In that case, we say this is an increasing linear relationship. Okay, increasing. Also called positive linear relationship existing between x and y. And if your scatter plot shows a decreasing trend overall, this is called a decreasing linear relationship, also called negative. And the second method we talked was the coefficient of correlation. Remember, the coefficient of correlation is a value between -1 and +1. I wrote two brackets. This means all values from -1 to +1 are possible. And if your R is positive, if your R is greater than 0, it's a positive linear relationship. Or in other words, increasing. This shape, as x increases, y also increases if your coefficient of correlation is positive. And if your coefficient of correlation is negative, we say it's a negative linear relationship. Or in other words, it's a decreasing linear relationship. Okay? So those are the two types of linear relationships. And then let's move on to point number 8. I have given you an example. This data set can be found in the lecture note uploaded on Canvas. In that data set, I have clearly defined X and Y. Y is the purity of oxygen produced in a chemical distillation process, and X is the percentage of hydrocarbons that are present in the main condenser of the distillation unit. The scatter plot is given. So if you see the scatter plot, it shows you an increasing trend. Okay? The scatter plot looks just like this. It doesn't have this equation, but it only has the scatter plot. That means the data points. So it looks like that. Means your x-axis is the hydrocarbon level in that example. And your y-axis is the oxygen purity. So it has this overall shape. As x increases, y also increases. That means, do you expect a positive or negative linear relationship? Explain. Yes, I expect a positive linear relationship, increasing linear relationship, because the scatter plot shows that as x increases, y also increases. By looking at the data set given, we cannot determine which one should be taken as x and which one should be taken as y if we don't have any proper subject knowledge. Because I don't see any of the two variables with a fixed step size. No fixed step size means we are not sure which one should be taken as x. If I had a fixed step size, I'm clear that that variable should be taken as x. But in this example, I have clearly defined x and y. So please make sure that they are read clearly. Let's move on to point number 9. Coefficient of correlation, R, equation, and interpretations. The coefficient of correlation is discussed as the analytical method to detect the strength of linear relationships. But remember that the coefficient of correlation will only detect the strength of linear relationships. It will not detect any other non-linear relationships. We said the coefficient of correlation, R, is a value between -1 and +1. If it is positive, it's a positive, that means increasing linear relationship. If it is negative, it's a decreasing or a negative linear relationship. But how do we actually calculate the coefficient of correlation? Well, of course, you can simply use your calculator. So this equation is not something you have to remember. But I'm going to write down the equation because that's the equation that your calculator uses in order to calculate the coefficient of correlation. So here's the equation. Coefficient of correlation is given by R, lowercase r. This is equal to the summation x minus x bar times y minus y bar, all divided by s sub x times s sub y. Now what are they? X means the variable x. What is x bar? X bar stands for the sample mean of the variable x. Y means the variable y. Y bar is the sample mean of y data points. Sx is the standard deviation of x. Sy is the standard deviation of y. And what is this symbol? That is the summation, sigma notation. You know it, right? So if I actually have a data set for x and y, all you have to do is, well, I have these data points. I have x data points and I have y data points. You can calculate x bar, which is the sample mean of all of these data points. You can calculate y bar, which is the sample mean of all of the y data points. Now from each x data point, I can subtract its mean. From each x, I can subtract x bar. Okay? So whatever this x value, I can subtract x bar. Whatever this x value, let's say x2, I can subtract x bar. I can do that for every single x value. Now similarly, I can subtract y bar from every single y value given here. So if the first reading is y1, I can calculate y1 minus y bar. If the second reading is y2, I can calculate y2 minus y bar, and so on. I can do it for every single y data point in this column. Now after that, what I have to do is I have to take the product between these two. Okay, that's what it says on the top. So I'm going to take the product x minus x bar times y minus y bar. I just have to multiply the first two readings here and I can write the answer there. I can multiply these two and write the answer there. And likewise, I have to continue for every single data point for these calculated values. Okay, I can find these values. And then I have to take the summation. I have to take the summation of all of these. Take the summation. That summation is the numerator of the coefficient of correlation. And Sx is the standard deviation calculated for all the x values. Sy is the standard deviation calculated for all the y values. And you know how to calculate those standard deviations and x bar, y bar values using descriptive statistics in your calculator. Okay? So basically, you know everything about this equation at this point. But we don't do this calculation as that. Your calculator has a single step to find the coefficient of correlation. So that's the calculation. And then we also have to interpret the calculated coefficient of correlation. So the very first interpretation is to see if it is positive or negative. If it is positive, the linear relationship is positive, which means as x increases, y increases. So if your r is negative, it means the linear relationship is negative, or in other words, as x increases, y decreases. Okay? But that's not enough. Because, for example, let's say I have x and y, and here's my scalar plot. So this is clearly an increasing relationship between the two variables. So I can see there's an increasing trend. Let's say I have another x and y combination. Okay, these are two different variables. Let's say this is x1, y1, and this is x2 and y2. Okay, new two variables. Let's say the data points are just like this. Well, this is also increasing, right? This is also increasing. This is also increasing. But compared to this one, x2 and y2 must be much significantly stronger compared to x1 and y1. So when we have a positive value for r, that is not enough by sign alone. I will also need something more than just the sign. Based on the numerical value of r, we can actually figure out whether it is a relationship like this or whether it is a relationship like that. How do we do that? Now I'm going to talk about only the absolute value. If your r is negative, you can transform all these interpretations into decreasing scenario. Okay? So I'm talking about absolute value of r. Okay? That is the positive value of r. So if this absolute value of r is between 0 and 0.3, we say there is no linear relationship, or there is a very weak linear relationship existing between x and y. Okay? No linear relationship, or a very weak linear relationship. That means if I go for the negative side, this should be between negative 0.3 and 0. Still we say there is no or very weak linear relationship. Alright, and then if your absolute value of r is between 0.4 and 0.6, we say we have a moderate linear relationship. Moderate linear relationship. And then the final interval for absolute value of r is if it is between 0.7 and 1. We say it's a strong linear relationship. So even within this interval, as you go up, the strength will be more and more. Okay. So for example, this scatter plot may have like r equals 0.7. This scatter plot, on the other hand, may have r equals 0.95 or something. Okay. So these are three intervals of r. They're very important. I will specifically see in the exams whether you have addressed these points when interpreting the coefficient of correlation. Of course, in this class, calculating the numbers will not be that important. We're going to always use technology. Of course, we have large data sets, and doing any hand calculations may not be practical. But more important point in this class is interpretation of those calculated values. Let's move on to the next point. Using the data given in point 8, okay, that means this data set regarding the hydrocarbon level, which is the X variable, and the oxygen purity, which is the variable Y. Calculate the coefficient of correlation between hydrocarbon level and oxygen purity. Interpret the calculated R. For your calculator, before calculating the coefficient of correlation, there's something very important to do for TI-84 CE+ or any other TI-84 calculators. Let's go to your calculator and do that modification now.
Here is our TI-84 CE+ calculator. Now I'm going to show you a step which is required to calculate the coefficient of correlation. It's enough to do this only one time for your calculator, unless you reset the memory of the calculator. What you have to do is you have to access catalog by pressing second and 0, and then you have to go down until you see diagnostic on. You can see there are two diagnostic functions. Diagnostic off is the first one, and the next one is diagnostic on. Select that one, hit enter, and hit enter again. On your screen, you must see diagnostic on done. Without this step, you cannot calculate the coefficient of correlation R.
Now we can calculate the coefficient of correlation. Please make sure there is something very important. When you enter the data, please double check your entries always, because even if you enter one data point incorrectly, especially this data set has decimals, and for example, you have 1.55 as one reading, and if you entered by mistake, it has 15.5 or 155, all your calculations will be incorrect. So after entering your data set, please go back and check your entries for all the calculations of this class, because in the exams, we of course don't do any hand calculations, and there's no way that I can assign you any partial credit if your final answer is incorrect. So obtaining the final answer correctly using technology is up to you. It's your responsibility, okay? So please make sure that the data are entered correctly. All right, we can enter the data set now, and we can calculate the coefficient of correlation. All right, let's do that.
Here's the calculator again. To enter the data set, I had to first press Stat, select Edit, select number 1, Edit, hit Enter, and I can now enter the given data set. We will enter X data points, hydrocarbon level data points, into the list L1, and oxygen purity, Y data points, into the list L2. So the first X reading is 0.99, enter. The second reading is 1.02, enter. The third X data point is 1.15, enter, and so on. I will enter the complete X data points into the list L1. All right, I entered all the X readings into the list L1, and now I'm going to enter all the Y readings into the list L2. The first reading is 90.01, the second reading is 89.05, the third reading is 91.43, and so on. I will enter all the Y readings into list L2. All right, I entered the complete data set into the calculator. Now I have to calculate the coefficient of correlation. To calculate the coefficient of correlation, I'll press Stat again, select Calc using the right arrow key, and then you can select number 4, linear regression AX plus B. Select number 4, linear regression AX plus B, hit Enter. Now here you have to define the lists where you entered your X data points and the Y data points. we entered all the X data points into the list L1. We entered all the Y data points into the list L2. Of course, those are the default list labels. In case if you entered those data points into different lists, make sure that you correctly define the list labels in front of X list and Y list respectively. There was no frequency list, so skip frequency list. We do not want to store regression equation either. Simply select calculate and then hit enter. Now you can see that y equals ax plus b, a equals 14.94, b equals 74.28, r squared equals 0.877. But for now, what we need is the very last line. R equals 0.9367. That's the coefficient of correlation.
0.9367. That's the coefficient of correlation for this data set between hydrocarbon level, which is the variable X, and oxygen purity, which is the variable Y. So how do you interpret this calculated value? There are three pieces. Okay, so the first piece is I have to see if it is positive or negative. So carefully read your output. If it is negative, there's a very small negative sign written before the value of the calculated R, and it's not very visible. I need to warn you. So read your output carefully. Okay. So of course this doesn't have a negative symbol, so it's positive. Okay. So the interpretation, the first part will be it's a positive linear relationship, or you can say it's an increasing linear relationship. Okay. It's increasing, or you can say positive. So that's the first part of the interpretation. The second part is I have to classify whether it belongs to the first group, second group, or third group. Okay. Of course, 0.9367 is between 0.7 and 1. Therefore, the relationship between X and Y of this example should be strong. Okay. So it's a strong relationship. Now, what's the third part? The third part is, we said R only quantifies the strength of the linear relationship. Okay? So it's an increasing, strong, not just relationship, but a linear relationship. So the term linear is required. Of course, whenever you interpret your calculated R, the third piece of this interpretation is always there. It is always fixed, because in this class, between two variables, the relationships that we detect will only be linear relationships. So this will always be present in your interpretation by default. So these two are the things that you have to handle, okay, and substitute the appropriate wording. So when I give marks for the homework and exams, if I ask you to calculate the coefficient of correlation R and interpret R, the calculated value alone will only get 2 points out of 5. 3 points will be assigned out of 5 to these three pieces of the interpretation. That's actually the end of chapter number 4, scatter plot and correlation. Now we can go for the materials from chapter 5. Whenever you have a reasonable linear relationship, at least a moderate linear relationship, the next natural step is that we would like to figure out what's the equation, the linear relationship equation between the X and the Y variables. So how do we do that? That's what we are going to discuss under chapter 5, regression equation. Under point number 11, we will see how to obtain the equation of the linear relationship between the two random variables X and Y. We said the equation is written as Y equals AX plus B. So all I need will be two equations to calculate A and B respectively. Of course, these two equations also you do not have to remember, because we are going to use technology to calculate A and B. But I'll just give you the two equations to figure out A and B, just for the completion of the discussion. So A is calculated using this equation, R times Sy over Sx, where Sy is the standard deviation of y, and Sx is the standard deviation of x, and R is the coefficient of correlation. Now, what's the relationship between A and R? Well, this is the relationship, of course, but we know that standard deviations are always positive only, because standard deviation is calculated as the positive square root of the variance. Variance is, of course, always positive. So these two values are always positive. If your R is positive, your A will be positive. Of course, in an increasing relationship, A means the slope. Slope should be positive. Okay? Slope should be positive if your relationship is increasing. And if your relationship is decreasing, that means the scatter plot has this decreasing overall shape. In that case, the slope should be negative. And it makes sense because the calculation of coefficient of correlation will say that R should be negative in that case. Okay? So that's the connection between A and R. R is only a value between -1 and +1, but there's no such restriction for A. A can be any negative number or any positive number. And then when you have the value of A, the calculation of B is very straightforward. B will be equal to y bar minus AX bar, where y bar is the mean of the y data points, x bar is the mean of the x data points. Alright, so when you have these two values, you can just plug in those values in this equation and write it as that. But when you write down the equation between two variables, you have to pay special attention to the way you write it. Now here's the reason. If you look at your data set, you will have x data points and y data points. Now let's say, for example, the first x data point is, we'll look at the same example that we discussed. The first data point in that data set is 0.99. And then first y data point is 90.01. Now we have an equation written like that. And I know the value of A, I know the value of B, those are just two values, real numbers. And what if I substitute a given x value in that equation? If I substitute a given x value in this equation, it will give me a y value, calculated y value. That calculated y value will be slightly different from the actual observed y value. But it is still a y value corresponding to the same x. The reason for the difference is, now here's my scatter plot. In the scatter plot, the straight line can be fitted like that, and that will be the best fitting straight line. Of course, when you calculate A and B using these two equations, this straight line is the best fitting straight line between x and y, because one can come up with, how about another straight line just like this? How about another straight line just like that? Well, the best fitting straight line is obtained by minimizing these distances from every single data point onto the straight line. These distances are minimized. That mathematical part cannot be explained at introstat level. That process is called least squares method, which requires a little bit of calculus. That's the reason we don't discuss the steps of obtaining these two equations in introstat level, because only college algebra is the prerequisite and we don't have any calculus as a prerequisite. So once we obtain this best fitting equation, it will not pass through every single data point in this data set. Well, it may pass through some data points. Maybe it's a couple of data points exactly lying on this straight line, but most likely the data points are slightly off compared to the straight line. Therefore, most of the calculated y values using this equation will be slightly different from the observed y values. So how do we write down two different y values? So the equation is not written as that. Instead, we write the equation as y hat to say these are the calculated values. Y hat equals ax plus b. Of course, you can find a complete column with y hat values next to the y readings of this data set. All I have to do is to just plug in these x values, each of the x values in this equation, and you can then calculate the corresponding calculated y values. Okay? So please make sure that you write down the equation as that with a little hat. This is read as hat. Okay? Y hat. All right, and again, the values of a and b alone are not enough. They are not very important. We can simply use technology and obtain these values. The important step is to interpret those calculated values of a and b. So let's see how to interpret those values in point number 12. Point number 12, interpretation of y hat equals ax plus b. The first interpretation is y hat. Y hat. These are the calculated values of the response variable using x values. Okay, those x values can be selected from the observed x values given in the table, or they can be just random x values for which we would like to predict the corresponding response variable. Okay, so I will say these are the calculated values of the response variable. Y hat. Then we have to interpret b and a of this equation. So how do you interpret b? Look, if your x is equal to 0, y hat value will be equal to b, right? So we say the calculated response variable, which is y hat, when explanatory variable is equal to 0, is given by b. So that term calculated y can also be replaced as expected y. Okay? So I would say expected value of the response variable which is the variable y when the explanatory variable which is the variable x is equal to 0. So when you write down your interpretation, please don't use the term response variable and explanatory variable. Instead, use the variable labels given in the question. For example, for the previous data set that we already saw, x is the hydrocarbon level and y is the oxygen purity. So I would say b, whatever this value, is the expected value of the oxygen purity when the hydrocarbon level is equal to 0. And then I need to interpret a, interpretation of a, which is a slope. But we don't just say it as slope. We don't even say it as rise over run. That's how you define slope in math classes, right? So what is this a actually when we say rise over run? Well, we'll see it slightly differently, okay? Now think about this equation. So the equation says y hat equals ax plus b. let's say now I'm going to increase the value of x by 1 unit. Now I will have a different calculated y value. So that y hat value will be different from previous y hat value. So I would say this is y hat 1, the y value calculated in the previous step, and now I'm going to increase the value of x by 1 unit. So the new calculated y value, I'm going to label it as y hat sub 2. Okay. Now what I did was I just increased the value of x by 1 unit. So earlier it was x, now it should be x plus 1. So if I put x plus 1 for this equation, it will be a times x plus 1 plus b. I'm going to label these two equations as first equation and the second equation. Now what if I subtract the first equation from the second equation? Now if I do that, on the left hand side I will get y2 hat minus y1 hat. On the right hand side, of course b and b will be cancelled. Look at this ax term. If I distribute this a inside the parentheses, it will become ax. And you have ax here. Those two ax terms will also be cancelled. I will only be left with a times 1, which is just a. So this is how we will interpret a of that equation. We don't say slope, we don't say rise over run. Instead we will say the expected change of the response variable if the explanatory variable is increased by 1 unit. Okay? So that's how we will interpret. A is the expected change of the response variable, which is the variable y, if the explanatory variable which is the variable x is increased by 1 unit. And again, please use the variable labels given instead of response variable and explanatory variable. There's another thing important that you have to observe. Here we say expected change, and here we say if x is increased by 1 unit. Why there's a difference between those two words? Expected change, we don't know if this y2 hat minus y1 hat is positive or negative. Or in other words, I don't know which one is larger out of y1 hat and y2 hat. So when I write y2 hat minus y1 hat, we don't know whether this quantity is positive or negative. If it is positive, I can write it as expected increase, and if it is negative, I can write it as expected decrease by dropping that negative symbol. But to be on the safe side, just write it as expected change. Now we will move on to the point number 13. Use the data set given in number 8 and obtain the equation of the linear relationship between hydrocarbon level and oxygen purity. All right, let's do that. We have to go to the calculator. And I had to figure out A and B and then write down this equation. Let's go to the calculator.
Here's our calculator again. We have already done this calculation earlier when we calculated the coefficient of correlation R, and I have the same output already on the screen. But in case if you don't remember, let me show it to you again. First, we have to enter the given data set by pressing stat, edit, number 1, edit, enter, and all the X data were entered into list L1, and all the Y data were entered into list L2. After that, you can hit stat, select calc, select number 4, linear regression, AX plus B, enter. Now you have to define the X list and the Y list. We entered our X data into the list L1, Y data into the list L2, and if you entered your X and Y data into different lists, make sure that those list labels are correctly defined. Skip the next 2 lines, select calculate, and then hit enter. Here's the required output. Y equals AX plus B. the slope A equals 14.9475. The y-intercept B equals 74.2833.
We are in point number 13. I need the equation y hat equals ax plus b, and if I read the calculator output, I got a equals 14.9475 approximately, and then b equals 74.2833. I need to write down the estimated equation. I will just replace these two values and write the equation properly. So I will say it's y hat, these are the calculated y values, and a equals that value times x, 14.9475 times x plus b, which is 74.2833. So that's the estimated equation, and now I have to interpret the slope. So what's the slope of this equation? Slope is equal to 14.9475. The slope is the coefficient of x. So the slope equals 14.9475. I need to interpret this. So in this example, our x is the hydrocarbon level, and y is the oxygen purity. So I have to use those variable labels when do the interpretations. We said slope represents the expected change of the response variable, which is this guy y, for a unit increase of the exploratory variable, which is hydrocarbon level. Okay. So I will write it as that. The expected change of oxygen purity, which is the variable y, when the hydrocarbon level which is the variable x is increased by 1 unit, is equal to 14.9475. Of course, the units of x are percentages, so you may write for this specific example that when x is increased by 1%, there are no other units given. And then I need to interpret the y-intercept. So the y-intercept is equal to the value of b, which is 74.2833. So how do you interpret the y-intercept? We said y-intercept is the expected value of the response variable when x is equal to 0. So we will write it as that. The expected value of the response variable is oxygen purity when the exploratory variable is hydrocarbon level, when the hydrocarbon level is 0, is equal to 74.2833. That's all. Let's move on to the next page. Point number 14. Percentage variability explained by the estimated equation, which is given by r squared. So earlier we said clearly not every single data point will be on the straight line. Okay. So this is a linear relationship. There is a linear relationship, very clear linear relationship, and I can obtain the least squares regression equation. Just some data points will be existing on this straight line. The other data points will be very close to the straight line, but they are outside of the straight line. Okay? So what percentage of this variability is explained by this straight line? That is given under point number 14. This percentage variability is given by R squared, where R is the coefficient of correlation. So if you square the coefficient of correlation and write it as a percentage, it's a general practice among all the statisticians. R squared is given as a percentage. That percentage is the percentage variability explained by this straight line. So the same calculator output of the calculation of R and the equation also has R squared, provided you switched on the diagnostics. So the R squared value for this example, which is given in fourth line of that output, R squared equals 0.8774. Now this is not given as a percentage in your calculator's output, but you have to convert that into a percentage when you write the answers, okay? So this is equal to 87.74%. So we say 87.74% of the total variability between the hydrocarbon level and oxygen purity is explained by this straight line. Y hat equals 14.9475x plus 74.2833. Let's move on to point number 15. For the previous example, hydrocarbon level and oxygen purity, R equals 0.9367. Calculate and interpret R squared. Well, that's what we just did, okay? But that calculation I straight away read from the calculator's output, R squared. Sometimes multiple choice questions, I might be just giving you the value of R, and I might ask you to calculate R squared. So all you have to do is take that value of R and square it and write it as a percentage, okay? And that's it. And sometimes I also ask that question in the backward direction. That means I might give you R squared and ask you to calculate R. If I do that, I will also give you the scatter plot. Because when you take square root, because if I gave you R squared, to calculate R, you have to square root the value that I gave you. Now when you take the square root of a number, you can take positive square root or the negative square root. We usually write plus or minus square root. So, to decide whether you should keep the plus sign or the negative sign, you have to look at the scatter plot. If the scatter plot shows an increasing trend, you keep the plus sign for the square root of R squared as the value of R. If your scatter plot shows a decreasing pattern, then you have to take the negative square root of R squared as the value of R, okay? Please keep that in mind. So we already answered point number 15. Then we can go to point number 16. So we had a data set and we calculated the coefficient of correlation. We obtained a regression equation connecting the two variables. We also calculated R squared. Now, what's the purpose of calculating that equation? For example, I would like to predict what happens for a given x value. If I use that specific x value, what will happen to my response variable y? I would like to know it in advance. That's the reason I need an equation like that. For example, if it's an equation between, say, wind speeds and rain, so for a given wind speed, what could be the rain? So likewise, for the example that we just discussed, the explanatory variable was hydrocarbon level and the response variable was oxygen purity. And so the values are given in a certain range. And let's say, for example, I would like to find the oxygen purity for a value of x, which is not found in this table. How reliable is my equation for that purpose? So we would like to evaluate the fitness of the regression equation for predictions. Of course, the reason why we obtain an equation between two random variables is the predictions. But how fitting is it for predictions? There are two possible ways for predictions. Those predictions are called interpolations and extrapolations. So we have to know what are those two types. Let's say here's my data set. These are my x values and these are my y values. Let's say the smallest x observation I have is 20. Let's say the largest x observation I have is 80. And I have all the data collected between those two values. And now I can obtain the least square regression equation, and it's a straight line equation, which means it will go from negative infinity to positive infinity all the way. So that equation will not necessarily give me the values between these two observed x values. Yeah, this is the minimum observed and this is the maximum observed x. Now, if I need to do a prediction for an x value, which is between 20 and 80, I need to find the y value. Say, for example, if I need to do a prediction for x equals 30, using the equation, I just have to plug in 30 for x of that equation, I will get a calculated y value. Now, this y value, let's say y hat sub 30 for this x. Now that's within the collected x values. This is called an interpolation. Interpolation, that's because the x value is between the minimum x and the maximum x of the observed values. Okay? So this is called interpolation. Let's say, for example, I would like to predict the y value for an x value outside of these two values. For example, if I need to predict the y value when x is equal to 90, I don't have any single data point including or something larger than that 90. But I would still like to predict the y value when x is equal to 90. Let's say this is that predicted y value. I will write it as y sub 90. Since my x value is outside of the observed interval of x values, this prediction is called an extrapolation. If I selected a value lesser than 20 also for x, since the minimum is 20, let's say I wanted to predict the y value when x is equal to 10, that calculated y value will also be called an extrapolation. Okay. So, there are two basic types of predictions, interpolations and extrapolations. Now we have to evaluate the fitness of the regression equation that we obtain for each of these two situations. Now this is how you will evaluate. If your R squared is greater than 80%, your estimated regression equation is good for interpolations. Good for interpolations. So we are done with interpolations. We have a way to figure it out. Then how about extrapolations? Now extrapolations will have some additional calculation. We say we need to do a residual analysis to talk about the reliability of the regression equation for extrapolations. Okay. Do a residual analysis. And based on the results of the residual analysis, we can say whether your equation is good for extrapolations or not. Let's now see how to do the residual analysis. So that residual calculation is discussed under point number 16. So we have our data set. So the data set has X values, which are the hydrocarbon levels, and we have the Y values, which are the oxygen purity. So the first hydrocarbon level is 0.99. First oxygen purity is 90.01. The calculated equation was y hat equals 14.9475x plus 74.2833. Now, like I said earlier, we can figure out a y hat value. So the y hat value is given by this equation. Now, y hat, let's do that calculation for x equals 0.99. So if x equals 0.99, the y hat value will be equal to 14.9475 times 0.99 plus 74.2833. Now we can find that value easily. I got y hat equals 89.0813. That's if you go for 4 decimals. Of course, the data set is given up to the second decimal only, so we can stop at the second decimal as well. But if you want to stop at the second decimal, please make sure that the rounding is done correctly. If you're not too sure if you're doing the rounding correctly, always go up to the 4th decimal to be on the safe side. Okay? So this is your y hat value. Now the residual should be calculated. We can calculate residual for every single data point. So I'm going to explain you how to calculate residual for x equals 0.99. So the residuals are defined as y minus y hat. Or you can also define this as y hat minus y. You just have to be consistent with every single data point. If you define it as y minus y hat, you have to do that way for every single data point. Okay? All right, so let's do that calculation for the first data point. Residual for the first data point should be y minus y hat. So the y value is from the table, 9.01. Minus the y hat value is equal to 89.0813. So you can obtain that answer. So I got 0.9287. So that's how the residuals are calculated. So this calculation can be done for every single data point. But we don't do it manually one by one. Instead, we can use our calculator and do a faster calculation of all the residuals at once. Let's go to your calculator and do the residual calculation.
Here's the TI-84C E+ calculator again. I already have the previously obtained output for the regression equation y equals ax plus b, a equals 14.9475, and b equals 74.2833. Please remember this equation. We are going to need the equation when we calculate the residuals. To calculate the residuals, we have to go back to the data set. To go back to the data set, I have to go to Stat, Edit, number 1, Edit, Enter. You can see that we have previously entered X data into list L1 and Y data into list L2. The equation is y hat equals 14.9475x plus 74.2833. Since x data are in list L1, in order to calculate all the y hat values, we can rewrite this equation as y hat equals 14.9475. Instead of x, we will now write L1 plus 74.2833. We will now calculate all the predicted y values into list L3. To do that, you have to first select the list label L3. You can see that now L3 is highlighted in black. When L3 is selected, below the table, you will see L3 equals. Now that's where we define our equation. Let's write down the equation this way. I will open parentheses, 14.9475 times x. X values are in L1, second 1, and then I will close parentheses, plus 74.2833. Our original equation was y hat equals 14.9475x plus 74.2833. We are going to obtain all the y hat values into L3. X values are in L1. So I wrote down the equation as L3 equals 14.9475 times L1 plus 74.2833. Now, when I hit enter, all the y hat values are calculated into list L3. What I need is not just the calculation of y hat values, but I need the residuals. Let's define the residuals into list L4. Select the list label L4. Once L4 is selected, you can see that L4 is in black. Below the table, you will see L4 equals. To obtain the residuals, I need to take the difference between y and y hat values. Y values are in L2, y hat values are in L3. So let's write down the equation as L4 equals L2, which is second and 2, minus L3, which is second and 3. Now I have L4 equals L2 minus L3, which means L4 equals y minus y hat, which should be all the residuals. When I hit enter, I get all the residuals calculated into the list L4.
So you saw how to calculate all the residuals. Those residuals, the calculated values, should be entered into this column. And you will see a question just like that in your first exam to calculate the residuals. I might ask you to calculate all the residuals, or I might just ask you to calculate one residual. Even if I ask you to calculate one residual, maybe you can do it this way, or you can calculate all the residuals using your calculator and pick the specific residual that I want you to answer. Let's move on to point number 17. So the point number 17, importance of residuals. Characteristics of residuals for the reliability of regression, especially for extrapolations. There are a few characteristics you should specifically pay attention. We say your regression equation is good for extrapolations if it meets these characteristics of the residuals. Okay? Good for extrapolations. If the residuals follow these characteristics. So the first characteristic is about half of the residuals should be positive, the other half should be negative. Of course, it makes sense because if it's your scatter plot, if this is your scatter plot, the best fitting equation should be just like that. And about half of the data points should be above the straight line, the other half should be below the straight line. So the residuals are calculated as y minus y hat. So the y hat value will be the value on the straight line for a given x value. Okay, some y hat minus y values, so the y minus y hat values will be positive, whereas the other y minus y hat values will be negative. So that's the first requirement. About half, or I would say 50% of residuals should be positive. I usually write this way, positive. And this means about half of residuals should be negative. The other half, I usually write it this way, negative. So that's the first condition required for the residuals. The second condition required is that the residuals should be normally distributed around 0. That means for all those calculated residuals, if you draw a histogram, that histogram should have a normal distribution around 0. Residuals should be normally distributed around 0. That means your histogram of residuals should look like this. Most of the residuals should be around 0. Just a few residuals will be very large and positive, and just a few residuals will be negative and away from 0. Okay. So that's the second condition, and there's another third condition. So the third condition is we also look at the residual plot. Now, what's the residual plot? The residual plot is a graph, and it also has x and y axis. The x-axis is the data point, whether it's the first data point, second data point, third data point, and so on. Okay, so data point number. That's the x-axis, and on the y-axis you have the residual. Of course, if you look at the data set given in that example, I have observation number on the leftmost column. So for the first data point, I can calculate the residual. So I can show that residual as the first data point. So for the first data point, the calculated residual was actually positive, so it will be a positive value. And for the second data point, if the residual is positive, it should be positive. If it's negative, it should be negative. And so likewise, we can show the residuals. Now that's called the residual plot. There's a specific requirement for the residual plot. Your residual plot should not show any identifiable patterns. Okay? That means the residual plot, the residuals, should be scattered randomly around 0 and within an even band along the x-axis. If your residuals showed some pattern, for example, let's say the residuals were drawing like this. That's not good, okay? And let's say the residuals had a straight line pattern, increasing straight line pattern. That's also not good. Or sometimes the residuals can have increasing and decreasing pattern, a sinusoidal. That's also not good. So if your residual plot shows that all the residuals are randomly scattered around 0 and within an even band along the x-axis, your residuals meet the third criterion for good extrapolations. So if these three conditions are satisfied by the residuals, we say your equation is also good for extrapolations. However, before talking about any extrapolations, first make sure that your R squared is above 80%, at least 80%. Because we say if your regression is not good for interpolations, it will never be good for extrapolations. So the first condition is that your equation should be first good for interpolations, which is guaranteed if your R squared is above 80%. And then we go for extrapolations. We'll move on to point number 18. For the hydrocarbon level and oxygen purity, the histogram of residuals and the residual plot are given below. comment on the reliability of the obtained simple linear regression equation for extrapolations. So here are the two graphs. I have the histogram to the left and residual plot to the right. Well, it's a small data set with just 20 data points. If I have a large data set, maybe I can see the patterns more clearly. So this question is actually subjective. If you see this histogram as a normal histogram around 0, well, you can say it satisfies this second condition. And if you see the residual plot does not have any specific identifiable pattern, then we can say it also satisfies the third condition. And also if you see about half of the residuals are positive and about half of the residuals are negative, then it also satisfies the first condition. So for me, it looks like both histogram and residual plot confirm these three conditions. Therefore, I would say, yes, my regression equation is also good for extrapolations. We already saw that it is good for interpolations because R squared was above 80%. Now we can go on to point number 19. In point number 19, I have given you a couple of residual plots. They are examples for bad residual plots. In the first residual plot, you can see that the residuals are increasing. We said a residual plot, to be considered good, it must have residuals evenly distributed along the x-axis. Of course, x-axis is the data point number. Whether it's the first data point, second data point, third data point, and so on. Now, in that given residual plot, the first residual plot, you can see that residuals are kind of like increasing. So these are the residuals, and you can see that there's an overall increasing pattern of residuals. Therefore, it is not good for extrapolations. And the next residual plot has a shape like this. So the residuals are like that. It's a parabolic shape for residuals. We said the residuals should not be having any identifiable patterns, but that one actually has a certain pattern. So the regression equation related to this residual plot will also be not good for extrapolations. Okay? And the third residual plot, it may or may not be good for extrapolations. It's subjective, but for a more advanced statistician, you can see that the residuals are like increasing, decreasing, increasing, decreasing, increasing, decreasing, like that. That means it is an identifiable pattern. In that case, the regression equation, which is corresponding to this specific residual plot, may also be not so good for extrapolations. All right, so that's it about those two chapters on regression, chapters 4 and 5. Thanks.